Welcome back to another episode of Black Guy Does Physics, where apparently our brains make farts. All right, let's get back into this because I don't know how to stitch these videos up, man. So I'm just going to post this as like part 2 or something. My brain just had a brain fart, and I had to just recollect myself because I didn't remember what the stupid X whatever was. Was, as you're going to see from the end of the other video, it's going to be, it should be the integral of, see, I'm trying to forget. I'm already forgetting already. It's x dm over the integral of dm. That's what it is. Because the center of mass, it's just mass times distance of all of them. So you're going to take up all the little masses. There's a way your books usually explain this junk, man. It's like the center of mass is you're taking all the masses times all the distance from a particular location divided by the total mass. That's basically what it is. That's why you could have the integration, because you're summing all the masses up together. So you're going to see, therefore, I could rewrite this as the integral of x dm over m, where m is the total mass. See? Because the integral of dm should be m. Makes sense to me. But once again, you're going to have the same issue that you had before. So you can see here, this and this does not match. This and this doesn't match. So if this and this doesn't match, that simply means that you have to rewrite this in terms of this. But luckily for us, we already did this junk up here. See that junk? We already know that dm is equals to lambda dl. Right? This is true. We know that dm should be equal to lambda dl. So I'm saying? Okay, cool. If that's the case, then we could substitute that junk in there. That would be equals to x lambda dl. Right? But you could substitute L for x because we're talking about the length, and x is representing the length. You also could substitute what lambda is, which was gamma, the integral of gamma x squared dl, or dx, sorry, because we're going to substitute that over m. And we know that gamma is something, so we could put gamma over m outside the integral of x cubed dx. And if you do that, then this becomes gamma over m, the integral of, not the integral because we're going to integrate it right now. You're going to have x to the 4th over 4 from, what is it, 0 to x or 0 to L? I think it's from 0 to L, I think. Same scenario. So gamma was, sorry for going back, I forgot what gamma, 3m over L cubed. So gamma was 3m over L cubed. So that becomes 3m over L cubed m times, at 0, the whole thing becomes 0. This whole thing becomes 0 if I stuff 0, because it's the top one, when you substitute the top, minus the bottom one. But if I put in 0, the whole thing becomes 0. So therefore you now have L to the 4th over 4. So that would give me 3L. So it's 3/4 the length of it. That would be my XCM. Nice and easy. I had a brain fart, bro. It was a stinky one too. Dear Lord. Once again, just slow down the video so you could see what I did there. It's just pure calculus, pure integration or whatnot. I think I might, let me do that again real quick because some of you might not have caught that. So the thing for the center of mass is this. It's the integral of this, the distance times the amount of mass. So that's just the general format. That's the general format. So burn it in your brains. It's the same thing if you're looking at it in the y or the z. If it's the y, then it's y dm over integral of dm. If it's the z, it's the z dm over integral of dm. The integral of dm is going to be m. Right? Once again, the problem that you're going to have is that you cannot integrate x with respect to m. Those two things don't work out. So what you need to do is that you're going to have to either rewrite dm in terms of x or x in terms of dm. We already know that since we have a constant, we have this as a constant, which is the density of the thing, and we know that the linear mass density would be the big M over L. Then if I took a small m over a small l, then that should also be equal to the constant. Therefore, dm is equal to lambda dl. So I substitute that in there. Once I have that, then L is just representative of my x, because if we go back to the figure here, you could see that x would be from where L is equal to 0 to there. So I could change dl to dx. And I also could put in the value for the constant for the linear mass density, and I substituted that. Then all I have to do now is just do calculus. It goes from 0 to L because of that's where we're starting from. So that's what you'd have to do. Hopefully that helped. Where am I? C. For an axis perpendicular to the page is the value of the rotational inertia of the rod around point P greater than, less than, or equal to the value of the rotational inertia of the rod around the rod center of mass. What the hell? For the value of the rotation, the inertia of the rod around point P greater than, less than, or equal to the value of the rotational inertia of the rod around the center. Oh, that's cake, man. Because you should understand that for rotational inertia, the moment of inertia, what they're asking you is if it's here or in the middle, which one is greater? Your brain should tell you that in the middle is going to be less. The reason why, it's because the weight is spread out less from the axis of rotation. That's the reason why. At the end, it will be more because, as you could see, the mass of the thing is spread out more from the axis of rotation. So whenever the mass of something is farther away from the axis of rotation, its moment of inertia goes up. So in this particular case, if I put this here at 3/4 L, the moment of inertia is going to drop compared to it at point P. It is what it is. And now we're at D. Is the rod if the rod is released from rest in the position shown, then the rod begins to rotate about the horizontal axis, perpendicular to the page point P. On the axis below, sketch the graphs of the net torque on the rod and the angular speed. Why the hell did I say rod like that? For a time rod is released until the time center of mass reaches the lowest point. Okay. So what's going to happen with the torque? So in my class, I usually tell some stuff like, see that it's going to be like this, or like this. One of those it's going to be. So the torque won't be linear. I don't think so. Can't be linear. So because that would mean that the torque would have to be directly whatever to the time itself. And anytime you have the time thingy, I don't think it's linear. So that can't be, and that can't be. The torque would have to be increasing if it was this one. If it was this one, and I don't think the torque would increase. The reason why is because as the thing drops, right? As the thing drops, then you're gonna have what is it? This grab here. Oh, I think there's a part F to this, which I'm missing. I didn't copy it. I don't know why. But let's say the thing is here. That's an ugly rod. Let's say the rod is here. Whatever. Let's say the rod is here. Then as this thing drops, the weight of this thing would be causing the torque. Right? This is your mg. And as you can see, it is the perpendicular part of the weight, this part, that's going to be causing the torque. But as this thing goes down, then this component is going to be getting less and 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 less, so that the amount of torque that is being produced by the weight is going to decrease. So it can't be the one that's increasing. So it's either this one or this one, something like this. So it cannot be this one, because this would indicate that the torque is dropping off ridiculously and then like that. So it cannot be this. So it has to be something similar to that, which I think it's like, it starts off like nice, almost horizontal, but not really, and that. What's happening with this one, the angular speed, the same concept, that, linear, that. Can't be linear once again, so those are gone. The angular speed isn't going to drop off, it's going to increase. Why? Because the thing is speeding up, broski, so it can't be that, and it can't be that. So it has to be increasing, but, oh, I forgot one, crap. It's, or that. I did this one, I forgot that one. This one. So this one would indicate that it's speeding up forever, or it's increasing exponentially. That doesn't make any sense, so that's the only one that's left back. So that's a way that I like hack how to draw graphs. It's only like 6 options you have, broski. And just use common sense to figure out which option is appropriate. And the reason why this is because the angular speed is increasing, but it will get to a point where it has some maximum speed that it could get, and then it would level off. All right, part E. As the rod rotates from the horizontal position to the vertical, is the magnitude of the angular acceleration of the rod increasing, decreasing, or not changing? It would be decreasing, I think. The reason why it would be decreasing, why am I speaking like this? The reason why it would be decreasing is because, as I explained before, the torque that is being produced will be less because the force is being less. And since the torque is equals to I alpha, if this thing goes down, if the torque is going down, then this is going down, because the moment of inertia isn't going to be changing. So if this reduces, then this reduces. I am sorry I left off part F off this. Yes, I'm horrible, I know. However, I don't know what to tell you, broski. You could just look at the solutions. And as usual, kids, unlike me a couple minutes ago, don't be a moo-moo.